All right, so thank you for coming. Happy Tuesday. Happy midterm week before spring break. Um, I've got an announcement for a thing I'm helping to lead. Are any of you in seminar, what is it, 350? One. Okay. So if you're in seminar 350, chances are you're going to read the Alan Turing reading soon or have done it. Um, and so I'm helping to lead this event called AI and the Turing test. I did it last semester and it was really fun. There were like 50 people there and it was great. This week it's the Thursday evening before spring break, so I'm not sure if we'll get 50 people there. But it would be cool. So the idea is um, so there's a test that you read about in this seminar reading of um, where Alan Turing is like, can we ask questions of a computer and judge by the end of it whether it is a computer or whether it is a person? And so we're going to run that. We're going to take what the reading says and try it out in real life with I'm going to be the person in the other room either answering things in a Google Doc as me or as ChatGPT. Um, so yeah, so it should be really fun. That is on Thursday at 5:30 p.m. Again, the Thursday before spring break. But you'll probably be on campus anyway for our class. So if you want to go get dinner and then come back at 5:30, it's in Galileo 201, which is the big lecture hall upstairs. Um, and it should be really fun. I think it went really well last time, so I'm looking forward to it again. So yeah, so that's happening. I'm doing it with physics professor Kintner and Professor Bird as well in languages. So it's a great group and I'm looking forward to it. Um, so I hope if you would like to come. Okay, so my plan for Thursday is we're doing a fun thing where you're going to walk around campus and look for graphs and then give me a sheet at the end saying, here are all the graphs. Um, Hopefully it doesn't rain. So we'll see. But yeah, so this is our pseudo midterm. Um, so the plan for today, I know I said maybe we'll start coding. I wanted to give you guys, because it's midterm week, a fairly chill week. So today my plan is we're going to finish the case studies for digraphs and then you can work on the homework and when you're done, you can head out. And then all I ask is that you turn in your digraph packets before you leave. Okay, so let me open that document. Okay, so let's see where we left off. So we talked about the competition graph, right? And we talked a little bit about the signed digraph. So maybe I just want to spend a little bit more time talking about it. Um, so maybe if you want to talk with your neighbors and kind of see what statements you can say about this. So we know that trying not to open one of the midterm exam documents. Um, Lecture notes, that's it. So I mentioned really quickly at the last time that if we've got this graph of sort of energy, this signed graph where we can say that this positive feedback cycle is where there's an even number of negative edges, and negative feedback cycle is where there's an odd number of edges. And one of the ones that the book goes through is the cycle of U, Q, and P, where the amount of energy used if the more energy is used, then that leads to a decrease in the quality of environment. And the decrease bit comes from the negative signed edge. So that's what that edge between those two vertices says. There's the quality of environment and population. And so that says if the quality of the environment increases, then the population increases, right? Because it's a better place to live. And so more people want to live there. And then if we have the size of the population and the amount of energy uses, I feel like this one is fairly obvious, right? Where if there's more people, then there's more energy use. So that's what that signed edge, the positive edge means. But the fact that there's a negative edge here means that this is a negative feedback cycle, because as the quality of environment increases, we get more people. As we get more people, the energy use increases. But as the energy use increases, the quality of environment decreases. And so when that happens, then there's less people, and then there's less energy use. So because there's an odd number of negative edges, then this is what we call a negative feedback cycle. So maybe let's look at a positive feedback cycle. So let's see. R and U is technically a positive feedback cycle. There's an even number of negative edges, even though they're all negative. So let's see if we can figure this out. So R is the electrical rate, so like the amount of money that you pay. And then U is the amount used. So as the rate increases, the amount of energy used is less, right? If PG&E raises the rates, then you're going to want to use less of it to not have to pay as much. And then going the other way, if you use more energy, this is the part that maybe doesn't make. So if you use more energy, then the rate decreases. This is why I don't really understand the graph that we have here. Does anybody have an idea? I think maybe this should be a plus. I don't know. Let's try a different cycle. Let's look at C, F, and U. So C is capacity. As the capacity increases, the number of factories increase because there's more capacity for buildings to use that energy. As the number of factories increases, we're building more factories. The amount of energy used also increases. And then as we use more energy, we're building out our infrastructure, so the capacity keeps increasing. So I can see that as a positive feedback cycle, right? As things continue to grow, we use more, capacity grows, we can build more things that use energy. Okay, so I would like you to maybe talk with your neighbors about the packet one, where the question is to list as many positive and negative feedback cycles as you can. I'm also concerned with that, but I would also just like you to spend some time maybe just talking through the graph of what's going on here. What can we say about researchers and science and budget? Okay, so talk with your neighbors. Go for it. Let's talk about this one. So most of you have gotten like the cycles. Any takeaways that you have from this graph? Any discussions about how science funding research works? Yeah. Go for it.
And bad science is published, the funding goes down, but it should probably still want something thanks to bad science.
Bad science published, funding goes down because why should we pay for this? But yeah, but we need more money to get better science. Any other takeaways? I thought the A to B was interesting, how if there's more jobs, then they don't necessarily want to be as picky about the people they hire, and so there's more poorly trained researchers. And then as there's more poorly trained researchers, then the amount of bad science you get more of because there's not as much rigor. Any other takeaways? Sure.
Need
A to H.
more jobs, right? Pressure, increase the budget. But I think assuming the budget is very high enough.
More jobs. Yeah. Pressure to increase budget. Maybe because if there's maybe like getting to the more jobs was the pressure to increase the budget. But now that we have more jobs, then maybe we don't need as much from the budget. We probably need to like sustain that, but not necessarily increase it. But
People get hired that these people want to get spent on payroll plus.
right. Yeah, and then maybe that's what creates this negative feedback cycle, where once we reach this point, then it maybe starts to decrease. Other ideas? Mm-hmm.
That will then allow increased public safety.
Right. Yeah. So if you do good science, then people are like, oh, wow, science is great. And if there's less problems, then we're like, oh, wow, science is great. Cool. So I hope this shows that, like, this is maybe more of an abstract graph problem, but where it's representing like real things in society. And so it's representing something really important. And I hope you take that with you, where even though it may be hard to understand at first of like what do the signs mean, but like being able to look at it and read it out can tell you something about our society, and we can represent that in graph form. This is one of the reasons why I think graphs are so cool and like why I think everybody should take this class, where it can represent um, something either concrete, like one of the problems that I saw in your Eulerian Hamiltonian homework was like a garbage truck route, or trying to go through and get every stop at every house and travel every street and then return back to the facility. So there's maybe like a concrete instance, but now over here with this, we've got maybe a more abstract thing that we're modeling as a graph. Okay. So then the last problem in the packet is the tournaments. So let's talk about tournament for a second. Okay. So remember we talked about the underlying graph, remember? Where the underlying graph, if we've got some graph like this, a directed graph, the underlying graph is just remove the arrows. Okay, so a tournament is defined as a digraph whose underlying graph is complete. So this is a tournament because this gives us K3, right? And so let's, so this, I think the one that I just drew is actually, we can apply this. So tournament kind of comes from, round robin tournaments where like if a team is in a round robin tournament, every team is going to get a chance to play every other team. That's kind of where we get this name. And so like rock, paper, scissors, for example. So let's say this is rock. Let's see. Rock beats scissors. And so if we have this edge, meaning if there's an arrow from A to B, then A beats B. And so rock beats scissors, scissors beats paper, paper beats rock. We've got ourselves a tournament. Okay, so there's the question on the packet, which is rankings. And so the way that we can rank things, so let's actually look at rock, paper, scissors. So we can take the graph that we have and just draw it a different way, draw it vertically. And so that means that the team on the top maybe wins more often, the team, and then draw it vertically like that. So we could say rock is on the top, rock beats scissors, which beats paper, but paper also beats rock. So we can just draw it vertically like that. There's a one in the book. Okay, let's see. So let me make sure I get the arrows right. And this goes that way. This goes that way. So we've got A, B, and C. We've got one in the middle too. And all the arrows go there. And then this is D. Okay, so if this is our tournament, it's a complete graph. It's K4, the underlying graph. And we can draw the ranking. Could draw like C. So C has only outgoing edges. So that means C wins. Like C beats everybody. The way we drew it was B, which goes to A, which goes to D, and then B also beats D, and C also beats D. and C beats A as well. We can draw the ranking like that. Um, so that's the, okay. So how many rankings are possible? Like how many ways can you draw that? I think that's an interesting problem. Um, I also want to just talk about like why rock, paper, scissors is such an interesting game where it's fun because every option has a chance to beat the other option. Like you, depending on which one you choose and your opponent choose, there is a chance to beat your opponent. Like rock can always beat scissors, but rock can also always be beaten by paper. Um, so I want to maybe, and I don't have like a formalized question for this. I just want us to think about it for a second of um, like what makes rock, paper, scissors fun? And I have a conjecture that the fun games like this have an odd number of vertices. And so maybe think of like variations to rock, paper, scissors of what happens if you reversed an edge or added a vertex. Does that still make it fun or not? Okay, so think through that with your neighbor. Two vertices have the same amount of outgoing. Mhm. So I think that's so for the packet problem, then that is like there would be two possible rankings. Like that's one possibility. It's a tiebreaker. You choose one, then you choose the other. Yeah. Mhm. Yeah. Yeah. Okay. So maybe first work on the packet problem and then we'll talk about rock, paper, scissors. That's the idea. You want to keep it down as much.
Yeah.
Yeah, so there's other, so I think there's decisions that you make. So what other decisions? Oh, the progress unit? Yeah.
Oh. Yeah.
I mean. The example in the book is like this toy example of the dog food brand, which includes Bumbo, Doggo, Lucy, Dogs, Fight Bits, etc. Every tournament has at least one path. Like, looking at some of yeah, so the answer that I forgot to mention that in the book says is looking for how many animals are in the path. So if you can draw the graph with the path going downward, then that's good. So yeah, so we find the path and we just redraw the graph.
Okay. So.
Okay, maybe 2 more minutes of just trying to figure out how many paths there are. And then we'll talk about rock, paper, scissors. Oh, man. Those are expensive. Over here. All right. What rankings did you get? Rank them from top to bottom. Draw, please. Top to bottom, and I'll just write them out left to right. Go for it.
B, C, A, B, B,
PCAED. Cool.
A, B, E, B,
ABECD. Yeah.
E, C, A, D, B.
Okay. Yeah. Okay. Any other ideas? Yes. Let's check against the. Oh yeah. Do you have one? EED. Okay. Let's check. We have ABECD. BCAED. BECAD. BABED. ECABD. We got them all. Hooray. Great job. Okay, let's talk about rock, paper, scissors for, I don't know, maybe 10 minutes. Um, so rock, paper, scissors is fun. And from like, why is it not fun? I feel like that's just luck though. But like on the playground, rock, paper, scissors is fun. Because if you had something like give me another page. Okay, I guess we're up here now. Like if you had something like rock, paper, scissors, so like rock, same rules, or paper beats rock, rock beats scissors, bless you, scissors beats paper, and then you've got like dinosaur, and dinosaur beats all of them. That's not fun, right? Because then everyone would choose dinosaur all of the time. So, um, is there a way to add dinosaur to make it not terrible? Yeah. What, like the asteroid? But dinosaur maybe could smash paper and scissors. But then but then I feel like you would choose rock or dinosaur all the time, and there would be no reason to choose paper or scissors, right? The mind game aspects of this. So there's, what is it? My friend sent me one of them. Um, ah, Let me see if I can pull it up. It involved Spock, Lizard Spock. Yeah. So rock, paper, scissors, lizard, Spock. Do you remember which way it went? Or so,
Paper, and then paper disproves Spock. Scissors first. I know it goes in a circle and then.
yeah. Let's see. Scissors decapitates lizard. Lizard eats paper. Okay, I'm not gonna redraw it. I feel like this is better. So, we've got rock, paper, scissors. Spock smashes scissors. Paper disproves Spock. Lizard poisons Spock. Lizard eats paper. Scissors decapitates lizard. Rock crushes lizard. However, Spock can vaporize a rock. So, what about this version? Why is this version fun? Because I think this is like maybe equally as fun as rock, paper, scissors, where you don't have one option that completely dominates the others. Yeah. 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 Same in and out degree. So Spock has two options to Spock can smash scissors or vaporize the rock, but Spock is also vulnerable to paper and the lizard. Whereas with the dinosaur, we don't have this same problem where um like in this version the in degree of dinosaur is 1, but the out degree is 2. And so since the out degree is 2, dinosaur is going to be the better option. So this is what is called. So when the in degree is equal to the out degree and we're in a tournament, this is called a regular tournament. So that's just the term that applies here when the in degree and the out degree are the same. And so something like the dinosaur is not regular because this property doesn't hold. There's maybe one other thing that I want us to look at. Um, and maybe this is seen most easily in like the traditional rock, paper, scissors. But what can you say? So in rock, paper, scissors, like you can make this cycle, right? Where scissors beats paper beats rock. So we can go all the way back around. Does that property also hold for rock, paper, scissors, lizard, Spock? Yeah. Um, and so the term that's used for, let me just redraw rock, paper, scissors, uh, rock, piece, paper, yeah, you know what I mean. The term for this sort of cycle happening is transitive. Do you have you ever heard of like the transitive property? Like if we have x equal to y and y equal to z, then we know that x is also equal to z. And this kind of property also holds with directed graphs, where if we can say there's an edge between R and S, and there's an edge between S and P, then there's also going to be an edge between R and S, or R and P. right? So the transitive property can also hold for directed graphs. Maybe not all the time. But in this case, since the edges go in that direction, it is. And so the thought that I'll leave you with is that I think that the odd number and like being regular works because it's a regular transitive tournament. That's my thought. Do you have any thoughts? Cool. Go play rock, paper, scissors. Okay, so we've got maybe 15, 14 minutes left till the end of class. So I would like your digraph papers once you're done with them. And the rest of the class, you can work on homework. Or if you're done with the homework, you can turn it in because it's due tonight.